instead of the other method. The other method has to do with integration by parts. Yes, integration by parts, whereby we will keep on integrating and that. But here we only need to differentiate once and second order derivative when we set t to be equals to 2. So we'll start looking at it now. They said the probability density function of gamma, according to the one given in the question, we have it as f of x equals to lambda exponential raised to power minus lambda x into brackets lambda x raised to power k minus 1 divided by k, where we have our x to be greater than or equals to 0 and x can also be less than 0. Now our parameter here, now we talk about this lambda, then we also talk about k. So we have k must be greater than 0, and as well this lambda too must be greater than 0. So now this is the distribution given to us in that question now, and this is what we are going to work with. But before we start working with this, there is a way whereby we can simplify it further, and doing that we're going to have this says lambda exponential raised to power minus lambda x into brackets lambda raised to power k minus 1 x raised to power k minus 1 divided by k. Then this also be equals to lambda raised to power 1 exponential raised to power minus lambda x lambda raised to power k into bracket lambda raised to power minus 1 x raised to power k minus 1 divided by symbol k. Now what we did here now is this. We say this lambda x has the power of k raised to power minus 1. Then we break it down. So for lambda to take the power and for x to also take the power. So we have lambda raised to power k minus 1 and x raised to power k minus 1. So doing this now, we can now see that we have lambda here. And we also have another lambda here, which is raised to power 1. This is the lambda here. This lambda is what we have here. Now, if we do this now, since we have a lambda raised to power k minus 1 here, we can see we have lambda raised to power k minus 1. Now, breaking this down, we split it to be lambda raised to power k multiplied by lambda raised to power lambda raised to power minus 1, and that is what we have here now. Say lambda raised to power k minus 1, we split it in order to have lambda raised to power k, then lambda raised to power minus 1. Now the fact that we have this now is because here now that we have lambda raised to power 1 and lambda raised to power minus 1, this lambda raised to power 1 and lambda raised to power minus 1 will cancel each other, so it will go. And from that now, it will remain exponential power minus lambda x, lambda raised to power k. Then we also have x raised to power k minus 1 with this symbol here, which is k into bracket k. Now from this now, we have the simplification, which is lambda raised to power k, x raised to power k minus 1 exponential raised to power minus lambda x divided by symbol x. So it means that this distribution given to us here, we'll simplify it to have this a better simplification. Working with this now will be more easier than working with the one given to us in the question now. Now we need to find the moment generated function of this distribution, which is gamma, and doing that we have MGT, which stands for moment generated function, equals to m subscript x of t equals to expected of exponential raised to power tx. So what do we do by this? What we mean by this is that this exponential tx now, we're going to use that to multiply this distribution. When we multiply this with this distribution and simplify it further, that will give us our moment generating function, and as such we're going to have this. Say mx subscript x of t equals to integral, which run from 0 to infinity, exponential raised to power tx lambda raised to power k, now x raised to power k minus 1 exponential raised to power minus lambda x divided by the symbol k, the x. Now if you look at this now, we can see that this is raised to power x. This lambda raised to power k has nothing to do with x. This is the only value here that has nothing to do with x, and therefore the fact that we have this now, we can even take it outside here because it stands as a constant. Now what do we do from here now? This exponential tx and this exponential raised to power minus lambda x, we can join these two together. I mean, we'll factorize it together since they are both exponential. Now this will lead us to the next slide, which will have integral 0 to infinity exponential raised to power minus x into bracket lambda minus t multiplied by lambda raised to power k, x raised to power k minus 1 divided by symbol k dx. Now what we've done here, that we've already joined the two exponential together, and then that gives us this. Now we still have our lambda raised to power k. Now in the next level, now we are going to bring out this lambda raised to power k. We'll treat it as a constant. Now we're going to do some little manipulation. Since we have a lambda raised to power minus t here, now we can also do something outside here. Now let me show you before we even explain that. So we have that's what we have here now. Lambda raised to power k divided by lambda minus t raised to power k integral 0 to infinity lambda raised to power minus t raised to power k divided by that. Now we have x raised to power k minus 1 exponential minus x, then into bracket lambda minus t dx. So what we've done here is just a little manipulation. This lambda raised to power x, we've taken it out, and this is it here. Now the question is that where do we get this lambda minus t raised to power k? Just a little manipulation. We can see that at this numerator here we introduce lambda minus t raised to power k, and at the denominator side here we introduce lambda minus t raised to power k. So this denominator can easily cancel this. We have 1, which means we've done nothing to what we have here, and the essence of that is to make sure that we have a probability of a sample space. And as we know that the whole probability of a sample space will be equal to 1. So as such, now instead of having lambda raised to power k, now we are dealing with lambda minus t. If you look at this here now, instead of having exponential minus x lambda, we are dealing with lambda minus t, which means we are not only dealing with lambda anymore, we are dealing with lambda minus t. So the distribution has become this now. Now we know that what is that in the next level we said the probability, the sample space of all probability will be equals to 1, and that is why when we have this f of x dx will be equals to 1. Therefore what happened, we have this. So integral 0 to infinity lambda minus t raised to power k divided by symbol k, x raised to power k minus 1 exponential raised to power minus x into bracket lambda minus t dx will be equals to 1. Why do we say this? Probability of all sample points, probability of all sample space of all sample points will be equals to 1. Now if you look at the probability density function of a gamma distribution, is exactly like this, just that the only difference is that we introduce minus t into this. Instead of t lambda raised to power k, now we are dealing with lambda minus t. Instead of raised to power lambda, we have a lambda minus t, which is the same thing as the probability density function. Now the whole sample space now will be equals to 1, and that is what we have here. Now if you notice that from this point of integration now to this dx is all the sample space we are talking about, and the whole that is equals to 1. So which means the next step we are going to have the same. Therefore everything we have here now, so therefore this becomes everything we have here now is going to give us this m subscript x of t equals to lambda raised to power k divided by lambda minus t, everything raised to power k, then multiply by 1. Yes, now we are dealing with 1 here because the whole of this integration here is the probability of all sample space, which is equals to 1, and we introduce it to this point, we have this 1 here. Multiplying this by this give us the moment generative function of gamma distribution. So that is the moment generating function of gamma distribution. So right from this point now, all we need to do now is to differentiate this moment generating function. When we differentiate this, that's the first derivative. But before we differentiate, we can rewrite this in another form, whereby this denominator will bring it up. Then we have a lambda raised to power k into bracket lambda minus 3 raised to power minus k. That is negative. So from that point, we say we have this now. Let's write the moment generated function. So lambda raised to power k into bracket lambda minus t, everything raised to power k. Now we can write moment generated function as this. The moment generated function now we can write it this way. So mx is t. So we have a lambda raised to power k into bracket lambda minus t raised to power minus k. What we've done here, we just bring this up, brought it up, then the power of, the sign of the power changed to negative. That is all we've done here. So in this case now, it will be very easier for us to differentiate this. In differentiation, we can use a product rule, because this is a function multiplied by another function. So we apply the product rule. Say the first derivative of m subscript x of t with respect to t, when t is set to 0, will give us the mean that we are looking for. So we are going to use a product differentiation. We are going to use product differentiation now, just like what we said the other time. So differentiating this now, we have a m subscript x of x, m prime of xt equals to minus k lambda raised to power k into bracket lambda minus t raised to power minus k minus 1 multiplied by minus 1. The derivative of this give us this. So this prime now indicate that we will differentiate this. This is the first order derivative. And what we've done here, in product rule we have when we are dealing with, let's say we are u multiplied by v, so the product rule is going to be u dv plus v du. That is, we'll differentiate this, we'll keep this, plus we'll differentiate this, we'll keep this. But first of all, what we did here is that when we differentiate lambda raised to power k with respect to t, is going to give us 0. So the whole thing in this part here is going to give us 0. Now plus we keep this lambda raised to power k. This is the lambda raised to power k here. Now when you multiply this minus k by the whole function, that's why we have this minus k here. And this is a function of a function. When you subtract 1 from this k, we are going to have minus k minus 1, and that is what we have here. Now finally we have to differentiate the function in this bracket. We are differentiating with respect to t. When we differentiate lambda, we have 0. When we differentiate minus t, we have minus 1, and this is the minus 1 that we have here. Now we differentiate this and keep this. When we differentiate this and keep this, our result is equal to 0. Now we keep this, we have this, then we differentiate this with respect to t, then we have a minus k of this function. Then the inner function gives us minus 1. Now if we use this minus 1 to multiply the whole of these, that will lead a positive value. Then we are going to have m prime of xt equals to k lambda raised to power k into bracket lambda minus t raised to power minus k minus 1. Minus k minus 1. So this minus here already neutralized the negative value here. Now we should not forget that this will become our mean when we set t to be equals to 0. So this minus t here will become minus 0 in order to get our mean. So from that point now we have m prime x of t 0 now equals to k lambda raised to power k into bracket lambda minus 0 raised to power minus k minus 1. And when this is 0, we are just going to have only here lambda raised to power minus k minus 1, and that is what we are going to have here. It says this is an mx of t we already have it here, lambda raised to power minus k minus 1. And if we do this now, if we factorize this, we can have lambda raised to power minus into bracket k plus 1, lambda raised to power minus k plus 1. Then if we bring this down, we're going to have k lambda raised to power k. If we write that, we have a k lambda raised to power k, then divided by lambda k plus 1. So k lambda raised to power k divided by lambda k plus 1. Now this will give us k lambda raised to power k divided by lambda multiplied by lambda raised to power k. And what have we done here? Now we split this. Say lambda raised to power k, this is lambda raised to power k. Now we have lambda, that is lambda raised to power 1. We split this so that this lambda raised to power k will cancel lambda raised to power k, and finally we're going to have e of m prime x 0 equals to e of x, which is the mean of gamma distribution we're looking for. So it becomes k divided by lambda, and that is the mean of gamma distribution. So we have k divided by lambda is the mean of gamma distribution. Now we need the variance of gamma distribution. Now, so the variance of a gamma distribution is what we are going to look for now. So we're saying variance is given as variance of s equals to e of x raised to power 2 minus e of x, everything raised to power of 2. Now this e of x here is the mean we got in the other time, which is k divided by lambda. Now what we need to do now is to find this e of x squared, and this we can also represent it in terms of differentiation. We said we're going to have variance of x equals to m prime x raised to power 0 minus m prime x of 0, everything raised to power 2. So you can see that when we differentiate this one and set it to be 0, give us this. Now we need to differentiate this further in order to get m prime, and see what we have here. We need to get e of x squared to get the variance. Now the variance, or the second derivative of m subscript x of t with respect to t equals to e of x squared when t is set to 0. In e of x squared 2, we also need to set t to be 0 for us to get m prime x. Now what do we use here? We use a product differentiation rule to get its derivative. What is the product derivative saying? We say we have m prime x subscript t equals to u dv plus v du. Now let's remind us what our first order derivative is. We say the first order derivative is m prime x of t equals to k lambda raised to power k into brackets lambda minus t raised to power minus k minus 1. So this is the first derivative, the first differentiation we got the other time. So from this point now, we need to differentiate this again using product rule, and this is the formula we're going to use now. Now this will lead us further. We say let u equals to k lambda raised to power x, this function here. Now when we differentiate k lambda raised to power x, we are going to have a 0 because we are differentiating with respect to t. Now k lambda raised to power x give us a 0. Now we'll move further and say let v to be equals to the other function here, k lambda raised to power k into bracket lambda minus t raised to power k minus 1. We'll differentiate that. We are going to have a k plus 1 into bracket lambda minus t raised to power minus k minus 2. Now that is when we differentiate this function here, which is what we've written here now. See, we are going to have exactly what we have here. So going further now, all we need to merge the whole thing together, and we will merge it together. We're going to have mx prime t equals to k lambda raised to power x times k plus 1 into bracket lambda minus t raised to power minus k minus 2 plus into bracket lambda minus t raised to power minus k minus 1. Using this formula, you can see our u from here, we have a k lambda x, which is this. dv, we've gotten our dv to be this, and that is what will slot into this place. Then we have plus what is here? V. Our v is this, we have it here. Then we have a du, and our du is 0. That is why we have 0 there. Now simplifying this further, we're going to have, what can we do here? We say lambda k lambda raised to power k, then we have k plus 1. Now we have this this du here. We've not slot in this du here. This du, we have this du here. So if we have this du here, and our du here is equals to 0, therefore if you use it to multiply this function, we are going to have into bracket 0 here. So if we say into bracket 0, the whole of this is going to be equals to 0. So going further now, we're going to have this saying m prime prime subscript x of t equals to k lambda raised to power k multiplied by k plus 1 into bracket lambda minus t raised to power minus k minus 2. Now we have that. Now since we've simplified this further, what we need to do now is to set our t here to be equal to 0. So it means anywhere we see t in this function here, in this value here, we are going to set it as we'll set it as 0. So going further, we have m prime prime x of 0 equals to k lambda raised to power k multiplied by k plus 1 into bracket lambda minus 0 raised to power minus k minus 2. Now since we've set our t to be equals to 0 here, we can then factorize negative here, so that we're going to have minus into bracket k plus 2. So let's do that and see. We say we have a m prime prime subscript x of 0 equals to k lambda raised to power k multiplied by k plus 1 lambda raised to power minus into bracket k plus 2. So we already factorize this minus. We factorize it out since our t equals to 0, so we have nothing to do with 0 here now. So there is something we can do here now, and what is that? The above equation can be written this way, say equals to k lambda raised to power k. Now k lambda raised to power k multiplied by k plus 1. Then we'll bring this down now, and the sign change to positive. So we have lambda into bracket k plus 2. Then equals to, we can split this now, and we're going to have k lambda into bracket k plus 1 divided by, we have a lambda raised to power k multiplied by lambda raised to power 2. So looking by this, lambda raised to power k here, we cancel this lambda raised to power k here. So what will remain now is saying m prime prime subscript x of 0 equals to k into bracket k plus 1 divided by lambda raised to power 2. And if you remember very well, so this becomes k plus k raised to power 2 divided by lambda raised to power 2. That is, we open this bracket with this k times k give us k raised to power 2, then k times 1 give us this k here. So now we've gotten our m prime prime x subscript x of 0, which is equivalent to e of x squared, that is expected square value of x. Now we slot in back to the variance formula. Now what is the formula talking about? So we say this is m prime prime x of 0 equals to e of x raised to power 2. That's what we said earlier. Now equals to e of x raised to power 2. Then we have a k plus k raised to power 2 divided by lambda square. So now we slot this into the variance. Now let's remind us the variance formula. We said variance of x equals to e of x squared minus e of x plus raised to power of 2. We've gotten e of x here the other time as the mean of gamma distribution, which is a k divided by lambda. Now our e of x square now is this k plus k raised to the power 2 divided by lambda square. So we'll substitute the 2 into this variance equation now, and we can also write this in terms of derivative, which is a variance of s equals to m prime prime x of m equals to 0 minus m prime x is 0 raised to the power of 2, and this will give us variance of s equals to k plus k raised to the power 2 divided by lambda raised to the power 2 minus lambda minus k divided by lambda, everything raised to the power of 2. You can see right from here we have a raised to the power 2, so we have to square the mean, and k over 2, k divided by lambda is the mean, so we square it. So when we open this bracket now, we're going to have this. It's a variance of x equals to k plus 2 divided by lambda divided by 2 minus k raised to the power 2 divided by lambda over 2. Now we have lambda raised to the power 2. Now we have the same denominator, which means we can divide this further. So we have k divided by k divided by lambda raised to the power 2. We have a k raised to the power 2 minus k raised to the power 2. That will be eliminated. So we are left with k divided by lambda raised to the power 2. So we have a k divided by lambda raised to the power 2. So the variance of gamma distribution is given as k divided by lambda raised to the power of 2. So this is the variance, and we've gotten the mean of gamma distribution. Now we look at characteristic function of a Bernoulli distribution. It's a characteristic function of a Bernoulli distribution. Now the probability mass function of a Bernoulli distribution, let's look at it and see what we have as the probability mass function of a Bernoulli distribution. This is given as probability of x equals to p of x equals to p raised to the power x, q raised to the power 1 minus x, where we have x to be equals to 1, 0, which means x cannot span more than 1. So we can have our x to be 0 or 1. It cannot be more than 1, and that is why it is Bernoulli distribution. Now let's look at the characteristic function. The characteristic function is given as say m subscript x of t equals to e of exponential iota tx. Now there are some other statisticians that will prefer not to use m to indicate this characteristic function. So instead of m, they use phi. Instead of m, we use phi to represent that. So we have a phi. So it means there are some textbooks or some other scientists that will use phi to replace this m. So that is a characteristic function of what is it called? Characteristic function of Bernoulli distribution. So merging this together, now we have this m subscript x of t equals to summation x equals to 0 to 1, like we said the other time. Then we have exponential iota tx multiplied by p raised to the power x, q raised to the power 1 minus x. So now this is the characteristic function. Now since we are dealing with Bernoulli, this is the probability mass function of Bernoulli. So we will multiply the two together. It gives us the characteristic function of a Bernoulli distribution. And as we know, this is raised to the power x and this is raised to the power x. We can match these two together. I will match it together. We have a summation x run from 0 to 1. Then we have a p exponential iota tx bracket close. Then we have a q into brackets 1 minus x. And don't forget our x span from 0 to 1. So when we use this summation now, wherever we find x, we substitute with 0, then plus whenever we find x, we substitute it 1. So this will give us p exponential t raised to the power 0, q raised to the power 1 minus 0 plus p exponential iota t Yeah, we have raised to power 1, q raised to power 1 minus 1. There is something we didn't put here. Under this p exponential t, supposed to be p exponential iota t. So it's supposed to be p exponential iota t. Then, since it is raised to power 0, definitely we know that that is going to be 1. And here we're going to have q will be left here. Now here we're going to have a 0, since we have 1 minus 1, which is 1, so that will go. So it will remain p exponential iota t. So what will remain here is q and p exponential iota t, and therefore the probability characteristic function of Benilite distribution is equal to q plus p exponential iota t. Or we arrange it this way: we said m subscript of t equals to p exponential iota t plus q. But we shouldn't forget that we said in some textbook this m is written as phi. Instead of m, we use phi. M, they use m for moment generating function, then phi for characteristic function exponential iota t. Now we look at the characteristic function of a Poisson distribution. So characteristic function of a Poisson distribution, the probability mass function of a Poisson distribution is given as p of x, as a p into bracket x, equals to summation x from 0 to n lambda raised to power x exponential raised to power minus lambda divided by x factorial. Now where x could be 0, 1, 2, 3, 4, infinity. And the characteristic function is given as m substitute x of t equals to exponential iota tx, then probability of x. Like I said the other time, this m could be written as phi in some other textbook. So instead of m subscript x of t, it could be m subscript x of t, that is q subscript x of t, as characteristic function. And what we are dealing with here now is to multiply this characteristic function by this probability mass function, which stands for Poisson distribution. Now slotting in this p of x, which is this function here, we're going to have this. We say exponential iota tx lambda raised to power x exponential raised to power minus lambda divided by x factorial. Now since we have raised to power x here and we also have raised to power x here, we can join this exponential and lambda together, so everything will be raised to the power of x. Now let's see. We say this is equals to lambda exponential iota t raised to the power x, then exponential divided by x factorial exponential raised to the power minus lambda. Now in Taylor series expansion, the whole of what we have here could be represented as exponential raised to the power lambda exponential iota t in Taylor series expansion. So just note that this value here, which is lambda exponential iota tx divided by x factorial, equals to exponential raised to power lambda exponential iota t, and this is a Taylor series expansion. There is a way of expanding this, and that is another topic on its own. So we just take it this way and we'll move on. So now instead of writing the whole of these, we'll slot in exponential raised to power lambda exponential iota t back into this position, and we're going to have this now. We said exponential lambda exponential iota t multiplied by exponential raised to power minus lambda. Now since you have an exponential here, we have exponential here. Now you can join these two together using a simple knowledge of indices, and having that, we're going to have a lambda exponential iota t. You can see we can factorize lambda. We can factorize this lambda. I will factorize this lambda. We're going to have a exponential. Yes, you see we've joined these two together now. These two exponential, we've joined them together by simple knowledge of indices. Now since we now have lambda here, we also have lambda here, you can simply factorize the lambda and we're gonna have m subscript x of t equals to exponential raised to power lambda into bracket exponential I eta t minus 1. So this is a characteristic function of a Poisson distribution. And like we say, there are so many textbooks prefer to use a phi subscript x of t in place of m subscript x of t. So phi subscript x of t mostly stand for characteristic function, whereby m subscript x of t stand for represent the moment generated function. But in some other cases, some people do not even bother to differentiate what they stand for. The most important thing is just to derive the parameter in question.